In this video, we are going to be covering the midpoint approximation for double integrals. And so it all relies on this formula here, which looks extremely scary, but don't worry, it is not scary. All right, I want you to remember back to regular old calculus where you were dealing with Riemann sums. And the way to approximate this area under the curve is using these rectangles, right? And this would be an example of a right Riemann sum. So in this case, notice how each rectangle, you're using the rightmost value as the height. And so the width of these rectangles, it's a constant, right? You're just moving across some change in x, right? This is like your change in x, right? And the height would be whatever your function is evaluated at this rightmost point, right? At the rightmost point. If you're doing the function height at the leftmost point, then that would be Riemann sum using the left value. And you can do a Riemann sum for the midpoint. So this would be an example of that. You can see that when I'm trying to approximate the area underneath the curve, the height of the function is the midpoint between these two values. So if I start at 0 and my next value is at whatever this point is, let's just make n be equal to 3. So if I start at 0, right, and the width of my rectangle is 2, so this distance right over here is 2, what I'm going to do is I'm going to take the average between the two values, so I get an x value of 1, and I take the height of that function there, and that becomes the height of my function. So I'm just going to multiply this width by this height at the midpoint. And I do it for every rectangle inside my interval. I want to find out the width of each rectangle, which is just the change in x. What I do is I take so if this is B, right, this is A, right, this is the interval upon which we're doing the area, right, finding the area under the curve between these 2 points. What we do is we take the distance between A and B, which is just B minus A, and we divide it by the number of rectangles that we want, which in this case, they labeled it as M for the X value and N for the change in the Y value. So imagine if we had a function f of x comma y that we wanted to integrate from 0 to 4 in the x direction and 0 to 4 in the y direction. And we want to split our interval in the x direction into 2 sections. And n is equal to 2, meaning that from 0 to 4, we're going to split it into 2 sections in the y direction. So in total, we have four different rectangles that we can deal with. And once again, just a reminder of what we are doing, just a little reminder of what we're doing, right? We're trying to approximate the volume underneath this surface. So how can we do that? Well, what the midpoint rule says is that, well, for every rectangle that you have, so notice how you go 2 units in the x direction and 2 units in the y direction, you're just going to take the midpoint of that and you find the height of the function at that midpoint, and you multiply it by the area of this rectangle, right? The area of this rectangle here. Because at the end of the day, if you're trying to find volume is equal to, in this case, because we're approximating it with rectangles, if you're trying to find out a volume of a rectangular prism, that's that we can say that this is the width, right? The width, this is the length right over here, right? So width times length, and then we can find out the height by just plugging in this midpoint value into our actual function, right? So imagine if we had like a surface that we had up here that we want to approximate. If I multiply this base right over here, which is essentially width times length, by the height, then I'm going to get this rectangular prism. I'm going to get this rectangular prism up here. And that's going to approximate the volume underneath this surface. So that's essentially the idea behind the midpoint rule. So it's important to note that the height, we get it from plugging the midpoint. We get that from plugging midpoint into the function. All right. So let's find out the midpoint for each of these rectangles. So if you're going 2 units here and 2 units here, what's the midpoint here? Well, take a look. right, the midpoint between 0 and 2 here is going to be equal to 1, and same for the y direction. So this first midpoint is at 1, 1. Let's move on to the next midpoint. The next midpoint here, well, what's the midpoint between 2 and 4? That's 3. And the midpoint between 0 and 2, the midpoint between 0 and 2 in the y direction is going to be equal to 1, right? So your y midpoint, your y value stays the same. Now the x value changes. Now we can find out the midpoint for this rectangle here, So the y value in this case is 3. Y midpoint here is 3. And the x stays 1. So this is 1, 3. And then this right over here would just be 3, 3. So what you would do is, for each rectangle here, every rectangle has a constant width and a length, right? So we can think about this as the base of our rectangle, right? The base is always constant. It always has a width of 2 and a length of 2, right? So when you multiply 2 and 2 together, that's going to give you a base area of 4. 4 is that area. Now, the height of that function, well, it's going to be given by f of 1, 1 plus f of 1, 3 plus f of 3, 1 plus f of 3, 3. And all of those values are going to be multiplied by 4 because they share a common base, right? The base area stays constant. So you can imagine that this 4 is like distributed among all these terms, right? Like 4 times f of 1, 1. That's the volume for this first rectangular prism. Then 4 times 1, 3. That's the volume for the second rectangular prism. And you just sum all these up, right? So I just factored out this area thing that they have in common. So the formula for this approximation is going to look something like this. And when you multiply length by width, well, you get that area we were talking about. So sometimes when you multiply delta x by delta y, some people write it as delta A to represent that. That's the area. And once we have the area, well, we have to focus on the height part. So how can we represent the height of that specific function? Well, I know that the height of the function has to be related to the actual function itself, right? F of x, y. But what I put in here, right? Well, what is the midpoint here? So x sub I minus 1, right? Well, let's say if we were focusing on this first rectangle here, x sub I minus 1 would be 0, x sub I would be 2. Take the average, and then you do the same thing for the y value, y sub j minus 1, which would be 0, y sub j, which would just be 2, and then the midpoint would be 0 plus 2 divided by 2, which is 1, right? It would be the average between these 2 points, and then you just evaluate the function at that middle point, 1, 1, right? Find the midpoint here in the x direction, find the midpoint here in the y direction, and you just plug it into the function itself to find out the height. And multiplying all of these together gives you the estimate of the volume. Now, if you make the limit as the amount of rectangle approaches infinity in both the x and the y direction, so the limit as n and m approach infinity, the limit as n and m, the amount of rectangles we create, go to infinity, right? We're going to be chopping up these sections into smaller and smaller rectangles. And so it's like the same thing with single variable calculus, right? If you take the midpoint here and you use that as an approximation, there's going to be some error, right? This is going to be the error, right? It's an over approximation here. But as the rectangle gets smaller and smaller, the midpoint becomes more representative of the height, and that error between the area that you estimate and the true area, or in this case, the true volume, is going to get smaller and smaller. And so that's going to be the formula for the double integral. Now, there's a couple more parts that I need to cover. One more part. which is how do I calculate x sub I minus 1, and how do I calculate x sub I? So x sub I minus 1 is going to be equal to your initial starting value, a, plus delta x times I minus 1. And x sub I is going to be equal to a plus delta x multiplied by y. And I can essentially copy and paste the same thing and apply it to the y value. So why does this work? Well, take a look at this, what we just did, right? So a is our initial starting point. What we do is we add essentially how much we skipped, which is delta x, right, the width, multiplied by I minus 1. So what I minus 1 is this, well, in this case, if I is equal to 1, then I minus 1 just gives you 0. So you just initially start at 0, and then if you take a look at x sub I, this is going to be 0 plus 2 multiplied by 1. So your next x value is 2. And you see how as I increases, we're essentially skipping 2 every time. So your previous value is x sub I minus 1, your next value is x sub I. And when you take the average, you get the midpoint, right? So this is essentially the formula for skipping in the x direction. And this is the same thing what happens in the y direction. And that's how you get this x sub I and x sub minus 1, which when you take the average of them, then you get your midpoint, which you plug into the function. All right, so I know that was a handful, but that's how you approximate double integrals. And when you take the limit as this approaches infinity, then it does become the double integral of f of x comma y dx dy from, let's say, a to b and c to d, right? Then it becomes this double integral.